Welcome back to your Topic 2 lessons on derivative rules and tangent lines. The last 2 days we really introduced the foundations of derivatives, where day 13 talked about secant and tangent lines and the tangent line problem or question, where how do you write a tangent line if you need 2 points to create a slope. And we had a way to approximate the slope at a single point. Day 14 really connected limits to derivatives and said that if you use a specific type of limit called the definition of the derivative, then you can actually find the exact value of the slope or the derivative or the instantaneous rate of change at a single point of a function. What we're going to do for the next few days is try to expand on how to use limits to find derivatives, but instead of using limits, we're actually going to go through and find shortcuts to avoid using limits. Most days are going to have a proof of a limit that shows us the shortcut, and then we'll generalize the shortcut from there. Today we're actually just going to get our very first shortcut. So let's take a look at our opener, which gives us the function x squared, and they ask us what the meaning of each limit equation below is. You don't have to do any calculations here. So take a quick second, try to explain the meaning in words of what each of those are telling us about the graph of x squared, and then I will summarize it after. Alright, we're back together. Let's take a peek. This first one is our definition of the derivative with x replaced with -3. So that tells us that we're going to be finding f prime of -3. And they give us, of course, that the answer is -6. So what does this tell us about the original graph f of x? Well, it says maybe we should do something like this. At x equals -3 on f of x equals x squared, there is an instantaneous rate of change of -6. What else could we have said? Well, you could have said if you go on x squared to the point when x is -3, the slope is -6, right? The derivative on f prime of x, or on f of x, is -6. Anyway, you want to relate back to x squared works for us as long as you talk about the slope at x equals -3. Well, how does that differ from our second one? Well, our second equation, instead of using an x of -3, just uses a variable x, where this is standing in for anything. And so, using our same syntax as before, we'd say that f prime of x this time is equal to 2x. So, how do we use this? At any x value on f of x equals x squared, the instantaneous rate of change is given by the function 2x. So if we want to know the instantaneous rate of change, if we want to know the slope or the derivative at any x value on the graph of x squared, we just replace x with whatever that x value is. If you wanted to know the slope at 10, we substitute 10 in here. 2 times 10, the slope is 20 at an x of 10. Now, these limit definitions here, and we talked last class, are very, very particular. Not every limit finds a derivative. In fact, there are only 3 definitions of the derivative, and they all use limits, that will find the derivative function for us, or at least that you are required to know in AP Calculus. Okay? Of course, remember, if you replace x with c, then the limit's going to find the derivative at a point at that x value. But if you use x in your limit, you're finding the derivative function, which is a function of x, an equation using x. The first definition shouldn't surprise you too much, right? This is our derivative function, and if you wanted the derivative at a point, you would replace x with, I use c here, where c is just standing in for a number. So that is our first definition. The second definition is using a difference quotient, and we talked about that phrase before. That phrase when we talked about slope, our y2 minus y1, right? This difference quotient. So to find the difference quotient, we'd say f prime of x equals the limit as x approaches a of f of x minus f of a divided by x minus a. Well, doesn't that look just like our slope, y2 minus y1 over x2 minus x1? And the general idea behind this, and actually I should probably call this a right here because that's what we're approaching. It's going to be a specific value, but the general idea behind this, if you wanted to take a look, is if you have some sort of graph and you have a point x comma f of x and a comma f of a, they are bringing x and a, right, x and a together, right, as x approaches a, as the value of x approaches the value of a, as those 2 points draw infinitely close together, calculate the slopes between the 2 points. The last one is our symmetric definition of the derivative. This one comes up, I think, the least often, and it's another one that uses the limit as h approaches 0, and it looks something like this. It says f of x plus h minus f of x minus h divided by 2h. And what ends up happening here is, again, giving you a nice cute little drawing. We have something like this, and let's say that you're trying to find the derivative at some value x here. So you're trying to find this. Well, you're nudging x a little bit to the right by adding h. That's a little bit to the right. This is our x plus h. And you're taking x and going a little bit to the left. This is like x minus h, right? And then you are performing that limit operation. Now, what this limit actually does is it really averages the left side and right sided derivative function. So it basically finds the derivative on the left, the derivative on the right, and then finds the average of those two. And this is a really good way to find a really nice approximation for a derivative, and that's actually what most calculators use. So when a calculator finds a derivative, and we'll learn more about that later on, they actually use this symmetric definition, which is why it's important to get exposure to it. However, the majority of the time you are going to be using these two definitions. Now, when I say use, on the AP exam, you never ever have to go through and actually use the limit definition, because you're going to have a shortcut to find the derivative that doesn't use limits. However, you are required to recognize this limit definition. So if they give this to you, you need to realize that is finding f prime of x. So being able to recognize these three, very important. You should commit those to memory, maybe make some note cards. But let's get into the main meat of today. So the first thing we're going to discuss is the notation of calculus. And unfortunately, calculus notation is a little bit convoluted. Once you get the hang of what means what, it'll be fine. But there was a little issue in history that made calculus a little bit more confusing, sadly. So before we get to the notation, there's a little bit of history that you'll need to know. And that history is between two men, Sir Isaac Newton and Gottfried Leibniz. Sir Isaac Newton, it shouldn't surprise you too much, is English. That's Sir right there. And he lived from 1642 to 1726, so he died at a ripe old age of 84. The man that we're going to suggest as his competition, Gottfried Leibniz, was born in Germany, and he lived from 1646 to 1716, so 70 years old. Also a pretty old age for that time. So both of them were born in the 1640s, both of them died in the early 1700s. But what is this competition that we're discussing? Well, let's start with Newton. So Newton was accepted at Cambridge College, Trinity College in Cambridge, really, in, I don't know, the mid-1600s. And he was able to complete his undergrad, his first 4 years, and then the Great Plague struck Europe. And really, the Great Plague struck England. The bubonic plague had been around for decades before that, but this was really the last major epidemic throughout England, right? Kills off, hundreds of thousands of people, not good. So they disbanded colleges, they disbanded any sort of gathering places, and, COVID shouldn't shock you too much about the precautions they took, and they really suggested that anyone that wanted to live, stay at home and don't talk to anybody. So Newton did that. He shut himself off from pretty much everyone and spent 2 years by himself at his house. This is in about, 1665, give or take. He's early 20s. And while he's there, he actually created the foundations for calculus. So he's 23 years old, right? This is 1666. And he says, I need some math to do something. Well, what was that something? He was really interested in planetary motion. And in fact, his big benefactor over the next couple of years was a man named Halley, and you might remember him from Halley's Comet, right? That comet that comes around every now and then you see up in the sky. So his benefactor, and when he reached out to him, he told Halley, he was like, hey, I have some idea on how to predict planetary orbits, and in particular when comets are going to come and go, and that was definitely of great interest to a lot of people, the motion of the planets at that point. And Halley said, well, that's pretty interesting, I'll finance you. So what Newton had done by himself in his early 20s is he's studying the skies and said, I want to figure out how these planets are moving in these weird elliptical orbits. And he's like, so let's do some math. He realized he didn't have the math for it, so he created calculus as a side note because it was just a means to an end, and then was like, hey, I want to publish a book about this planetary motion. And so in 1687, so this is about 15 years, about 20 years after, he publishes his first main and huge novel called the Principia. And it was the first time that his Newton's 3 universal laws of motion, you've probably heard of them, were ever written down. Calculus was mentioned in there, but it was a side note. It was never called calculus. It was a super dense book too, which probably didn't help him in the long run, but he basically, as he went through, he's like, here are these laws of motion, here are all my proofs for it, and within his proofs, buried down there, was what's known as a geometric approach to calculus. So he did everything we did with calculus, just using graphs and geometric drawings instead of actually using like symbols and notation. There were symbols and notation, but that didn't interest him since he had to make those up. He just put things that he thought people could understand. So what's going on in the rest of the world? Well, we have Gottfried Leibniz, who he was a super prolific writer, philosopher, mathematician, doctor. This guy did everything. And he was a big publisher too, in terms of he liked to publish all of his work. He actually wrote works in Latin, French, German, English, Italian, and Dutch. He was fluent in all of those. And what did he write his works on? Well, biology, psychology, math, medicine, linguistics, and more. He was all over the place. So in about 1674, and that's about 15 years after Newton, he has the idea of calculus as well. He published his work in 1684 and published it all about calculus. It wasn't calculus as a side note. This is this new field of mathematical study. Now, calculus really means to calculate, right? It's kind of an unoriginal name, which goes in the line with math. You even see the word calculus show up in books. So he went through the calculus of the project. He went through the calculations. So he published his calculus theories and his calculus math in 1684 and was immediately hailed as this huge genius, right? People are like, wow, Leibniz is insane. Look at what he's done. He's revolutionized the way that we can think about math. Well, that didn't really bother Newton because he hadn't heard about it, right? This is in the 1600s. So once word kind of starts trickling into England about this guy that published calculus, Newton goes, well, wait, why is this a big thing? I did this like 15 years ago, right? Now, Principia, 1687, did actually come out after Leibniz published his book in 1684. However, Newton was like, but I've been talking about this for 20 years. Like, why is this a big deal? So at this point, he decides to give a full account of his calculus. And in 1704, he puts out his full algebraic approach to calculus too, where he talks about his notation. It was called fluxional fluxional notation, puts it out in 1704, and then things got crazy. Because once that's out there, now we have this competition between those that supported Leibniz, generally the German-speaking countries, and those that supported Newton, which tended to be really the rest of Europe, saying, well, wait, who should get credit for this? And you're like, well, it's just credit, who cares? Well, it's credit for a really big idea that's kind of revolutionizing things, and so they both wanted the credit. So what ends up happening is Leibniz dies in 1716. In 1711, a tribunal was actually put together to basically put Leibniz on trial and say, hey, we think you actually stole ideas from Newton. We think it was like a friend of a friend of a friend that talked to Newton, that talked to someone that talked to you, and you're like, oh, that's what he's doing, so I'm going to take it and publish it. And in fact, there was a mathematician, L'Hopital, that we'll get back to later, a French mathematician, who basically tried to rewrite Leibniz's work in more user-friendly language and said, here's this awesome work that Leibniz came up with. Oh, by the way, it's pretty derivative, pun intended, pretty derivative of Newton, what he did 15 years ago. But that was in kind of the early 1700s too, so that kind of threw some fuel on the fire. But either way, Leibniz dies in 1716, but the controversy didn't stop. In fact, it really split the mathematical, the mathematical guilds of Europe for several decades. And so what ends up happening is the German-speaking countries used Leibniz's developments, which were essentially the same as Newton, except because they did these independently, Leibniz used completely different notation. So the German-speaking countries used this Leibniz notation for decades, and they're like, okay, here's what we're going to do, here's how we're going to come up with all of our theories. But in the meantime, we have the English side of things that is running with Newton and slightly changing his notation, but either way, using the Newtonian notation also for decades. And they don't reconcile until really the late 1700s. I mean, we're talking close to 100 years. And at that point, it was just too late to change notations. Half the people are using Leibniz, half are using Newton, and so what do we have now in our present day? Well, we have two notations that essentially mean the exact same thing, and because they're both common, you're expected to know both of them. So let's take a look at those two different notations and see if we can correlate what they mean with each other. So, on the Newton side of things, we have the phrase, take the derivative of a function. He didn't really have a way to tell somebody to do that. You would just say, find the derivative of a function. Leibniz, though, did. Leibniz had this notation, d dx. So we read it as d dx, even though it's d over dx, d divided by dx. We don't really want to think of that as two separate parts either, right? We're not thinking of it as d is one part and dx is another, though they kind of do mean separate things. He treated this as one whole operator. An operator is acting on something, and it means take the derivative of a function. So if you see d dx of x squared, you should read that to yourself as find the derivative of x squared. Well, we actually did that up above. We found the derivative of x squared is 2x, so we could probably fill that in. Take the derivative of x squared, well, that's equal to 2x. Jumping back to Newton, he has his f prime of x, or you could see it as y prime. You can leave off the of x. You could also just see it as f prime, right? Function notation or not. And those f primes right there mean the derivative. So if f of x equals x squared, then the derivative f prime of x is 2x. Leibniz also has something similar. He has his dy dx, which also means the derivative. So when you see d dx of x squared, take the derivative of x squared, then you could say the derivative is 2x. And so these two, although they look similar, are slightly different. One way you could keep track of it is you could think of this right here, where this says take the derivative of y. And then you have your final notation, dy dx, which means the derivative of y is 2x. So that would be another way to keep that straight. It might be worth noting, too, if you care, that this wasn't Newton's original notation. Newton actually used his fluxions. He put a little dot over the top, and sometimes that still is used, especially in physics. It wasn't until Lagrange, right, another French guy, came through and rewrote his notation and that was in, I don't know, late 1700s, 1787, like 100 years after Newton, that we started using this prime notation instead of the dot over top. So it's Newtonian notation, but with a twist. Okay, last but not least, f prime of a, what does that mean? Well, that means the derivative at x equals a. So an example, if f of x is x squared, and we know that f prime of x is 2x from the opener, then to find f prime of 3, that would be 2 times 3, which is 6. So the derivative at x equals 3 is 6. In Newtonian notation, we know that dy dx means the derivative, right? We see that right up above. And then you'll see this long line right here, vertical line, and then x equals a. And this means the derivative at x equals a, or maybe such that x equals a is a better way to read it. That's our set notation. And then we could also write it another way. Sometimes you'll see it as dy dx of a, and that's very similar to like f prime of a, right? Function notation. And again, that means, of course, the derivative at x equals a. So we're going to use this interchangeably, and you're going to go back and forth and back and forth. General rule of thumb is whatever notation the problem starts with is the notation you tend to use. You do not lose points by just randomly switching notations. You can use either one, but you do need to be comfortable with both. It turns out that the Leibniz notation is actually, I think most people would agree, a little bit better than the Newton and Lagrange notation. It does a better job of showing the different variables that are involved, and we're going to break down what these different variables mean eventually, not quite yet. But it shows all the variables at once, as opposed to this f prime, which can be a little vague, doesn't tell us what the input or output variable is, like this dy dx over here. But be comfortable with both. Now that we are comfortable with the notation, we are going to get our first shortcut. So although taking the derivative using those three definitions, using limits, right, is super fun. Remember how it took up like 10 lines every time we did one derivative? It's kind of impractical if you have to find the derivative of a lot of functions or even just one function. So the first rule we're going to begin with then is the power rule. The power rule is boxed right here. Very exciting. Tells us if we have f of x equals x to the n power, and this is a polynomial, generally, it does not have to be though. So some examples then, right? Polynomials, so you could have x to the third, x to the seventh, x to the 100th, something like that. But it isn't restricted to polynomials. We could also do things that aren't polynomials, that just have that form, x to the n that are not polynomials. Okay, well, we could have x to the 1/2, right, our square root function. We could have x to the pi. Ooh, that's pretty crazy, right? X to the pi power. That's not even rational. That's irrational. We could do anything like that. So as long as it's x to some power, you can write it as x to some power. Then our power rule tells us that the derivative of this function, without using any limits at all, which is the coolest thing since sliced bread, though this was around since before sliced bread, is you take the power, which is n, and you drop it down front. It becomes a regular number, n times. X is still there, but it's no longer the power n. Now the power is 1 smaller, to the n minus 1. And that's it. No limits. If they say find the derivative function, you drop the n in front, reduce the power by 1, and you have found your derivative function. No limits? Oh yes, it kind of makes you even more angry at your independent practice from last class, because this is so much easier. So how do we use it? Let's put this into numbers, I guess. If we have the function f of x equals x to the 4th, and we're asked to find f prime of x, well then you'll have to notice that our n up here is 4. So when we take the derivative, the 4 comes down in front. We reduce the power by 1, and my derivative function becomes 4x to the 3rd. The end. There's the derivative function. No limits. We went straight from the start to the end. Haha! Let's look at another. If we're given g of x equals 1 divided by x to the 3/2, find g prime of x. Well, in order to use the power rule, we need to rewrite it so it's x, top of a fraction, to a power. Otherwise, if we aren't able to do that, we have to go back to our limit definition. The limit definition always works, it's just really long, so we might as well use this shortcut when we can. So we need to rewrite this as x to the n. We know how to do that though. We bring this up and it becomes x to the negative 3/2. Whenever you move the position of x to a power in a fraction, then it changes the sign of the exponent. Well, now we can use our power rule. We take negative 3/2 and we write it down in front, keep x, and it's x to the negative 3/2 minus 1. Making sure we're comfortable with that. If I'm going to do negative 3/2 minus 1, we probably need to give them common denominators, yeah? And so this becomes x to the negative 5/2. There we go. Now, full disclosure, you can stop here. This is great. That is the derivative. Sometimes on multiple choice questions, they may simplify this a little bit more, or you may actually have to use this with what we mean is evaluate this at some number, and to use it, you might have to be comfortable with rewriting. So how do we rewrite this? Well, we take this x to the negative 5/2, and you probably know that mathematicians aren't a big fan of negative exponents, so we make it a positive. I don't know why I wrote 3/2. That should be 5/2. And then, of course, we can combine those together, multiply the top, multiply the bottom. We end up here. And then last but not least, we might want to remember what a 5/2 power means. It means x to the 5th, but the 2 comes over and serves as the index of our root, so it's the second root of x to the 5th, or hopefully you remember with roots you can just leave the 2 off and it's just the square root of x to the 5th. Any of these answers here would receive full credit for the derivative. Any of them. They're all right. I would probably stop with this first one, but if you needed to use it or rewrite it, make sure you're comfortable with the process. Now, there are a couple other derivative rules we're going to cover today. I think you'll need all of these at some point today. So let's get to it. The first one has to do with constants. If you take the derivative of a constant, before we even talk about the answer over here, you should know the derivative of any constant, because a constant, and we'll just take a look at a cute little graph over here. Let's say I have the graph of a constant y equals c. Here is a constant. If you want to find a function that describes the derivative of this graph at any point, well, we should probably look at the slope at any point. What is the slope at this point right here? Well, the slope of the graph is flat. The slope is 0. What's the slope over here? 0. What's the slope over here? 0. Therefore, it shouldn't surprise you that the derivative of a constant is always 0. A couple examples of that. If they tell you that f of x equals 3, that's like your horizontal line y equals 3, and they want to know the derivative function of that is just 0. Well, what if you had two functions adding together and they wanted the derivative of each one? Well, the derivative of x squared, let's use that power rule. The derivative of x squared, the 2 comes down in front. X, we reduce the 2 by 1 and get 1. Okay, plus, let's take a look at the second one, e squared. Well, you might think this would be 2e to the first based on the x, but you'd actually be wrong, because e squared is a constant, right? E is 2.71828 whatever to the second power. That is a constant. If you were to graph this, it would be that horizontal line again. And so if you're a constant, you do not use this power rule that we did over here. A constant always has a derivative of 0. Which means then that our final answer here is just 2x. Second additional rule. This rule is actually a pretty powerful one, and it tells us that if you have two functions adding or subtracting together, then you are allowed, if you're asked to take the derivative, then you are allowed to find the derivative of the first one and the derivative of the second one separately. I hesitate to use the fact that we're distributing this inside because that's not what really is happening, but you could think of that if you want. What's it mean? Well, I think I just told you, but we could say, I don't know, instead of finding the derivative of one complicated function, find the derivative of the individual pieces. Now this is only true for addition and subtraction. We'll find that multiplication and division gets a little bit crazier. So let's put this into words, or I guess let's put this into action. So if you're given f of x equals x to the fifth plus x, then let's find f prime of x. Notice that this is one big graph. I actually don't know what that graph looks like. It could turn 5 times or 3 times or 0, I don't know. It's definitely going to be a weird graph though. However, if you're not sure about the slope of that, then let's go ahead and split this into smaller pieces. So f prime of x is actually going to be equal to taking the derivative of x to the fifth and then taking the derivative of x, each part individually. Instead of viewing this as a whole, it's saying just look at the graph of x to the fifth and find that slope, then look at the graph of x and find that slope. Well, the graph of x to the fifth is going to have a derivative function of 5x to the fourth. Drop the 5 down, reduce the power by 1. The graph of x is a little bit weird. You're like, well, there's nothing up there, so is the derivative 0? Well, I don't think it's 0 because you know what the graph of y equals x looks like. The graph of y equals x is a diagonal line, and it has a slope of 1, up 1 over 1, and has that slope everywhere. A linear function always has a constant slope. So to me, this slope should be 1. Well, why is it 1? Well, let's put that invisible 1 that's up here, and then let's work through the math. The 1 would come in front, power rule, x, reduce the power by 1, that's 0. And if you remember your properties of exponents, anything to the 0th power is 1, and 1 times 1 is just 1. If you thought about this and said, oh, I know the derivative of this function, it's 1, and you just put 1 there, that's great. Again, the AP exam is curious about your setup and your answer. The rules you use to get from the setup to the answer are totally up to you. Let's look at one more. Take the derivative, d dx, take the derivative of x to the 1/2 plus pi to the negative second. Again, we're going to take the derivative of each individual piece, and full disclosure, I'd probably skip this step where I write the 2 d dx's in here. I just wanted to show it for, I don't know, full disclosure's sake. Derivative of each one. 1/2 comes in front. X, we need to reduce 1/2 by 1, and hopefully you're comfortable doing 1/2 minus a whole. You can always give common denominators, but I think pretty quickly you're going to realize that's negative 1/2 plus pi to the negative second. Well, would that mean we do negative 2 pi to the negative 2 minus 1, negative 3? No, I don't think so. I think pi is also a constant, right? This is 3.14 to a power. That is all a constant, and the derivative of a constant is 0. We are going to clean this up a little bit. I think it's good practice. X to the negative 1/2 is brought to the denominator. We don't need the plus 0 anymore. I think this becomes 1 over 2x to the 1/2, or finishing it off, 1 over 2 times the square root of x. Again, perfectly acceptable to stop here, but you should be comfortable simplifying. Last one. The derivative of a constant times a function is equal to a constant times the derivative of the function. And this one always throws people off, and understandably so, because what you're going to be tempted to do is you're going to be tempted to see a constant and say, oh, we learned that the derivative of a constant is 0, and then we can multiply it by the derivative of this guy right here. But I can show you right away that that's not going to be the case. Imagine you were to take the derivative of the graph, or the function, 2x. Again, visualize the graph. 2x goes something, goes right through 0, 0, something like this, and it has a slope of up 2 over 1, right? Y equals 2x plus 0 has a slope of 2 over 1, which means then, I don't know why, that's supposed to be a 2, it wasn't a great 2, which means that the derivative of this, because the slope is up 2 over 1 everywhere, the derivative has to be 2. I mean, that is the answer. That is the slope at any point on that line. It's up 2 over 1. But what I've seen people tempted to do at the beginning is they say, oh, it's 2 times x. The derivative of 2 is 0. The derivative of x, we saw this before, is 1, so I get an answer of 0. And clearly, that is not right. This graph does not have a slope of 0. Slopes of 0 are horizontal lines. And enter our derivative of a constant times a function. Constant times a function means when you take the derivative of c times f of x, you want to keep the constant the same and just take the derivative of f of x. So a constant multiplying by a function, the constant just hangs out. It's actually not going to change our result. Let's look at two of those examples and then you'll get a chance to practice. First part, d dx of all of this. Well, I'm going to rewrite this quickly as d dx of 2x cubed plus, I'm going to bring x squared up so it's written in the form of x to the n, or x to the negative second. And then we don't have a division rule, but we might recognize that as a constant, right? We can rewrite this as 1/6 times x to the fifth. And now these fit all of our rules. d dx of 2x cubed. Well, how are we going to do this? The constant is going to stay here. It's going to ignore everything else, and we're just going to work the derivative of x cubed. The 3 comes down, x, and then we reduce the power by 2. Let's work the second one. Plus, we can think of an invisible 1 here if you want, and when we work x to the negative second, it becomes negative 2x, reduce the power, smaller, so negative 3, and last 1/6, and same thing, 5x, reduce the power to get 4. Are we done? Sure, you could be done here. However, most people I think would clean this up. 2 times 3 gets us 6. A positive times a negative gets us a negative 2, and we could maybe even rewrite, we could bring down the x to the negative third, so 2 divided by x to the negative 3. 2 stays up, it has a positive exponent here. And then last but not least, 1/6 times 5, 5/6 x to the fourth. And that looks pretty good. The question will get asked at some point, wait, if I'm doing the derivative, if f of x equals 2x cubed, can I just go straight to, well, I know the 3 has to multiply by the 2, that's 6, and then reduce the power by 1. Can I go from there to there? Yes, please, I hope you do that. It is nice to illustrate the property here that tells us we keep the constant out front and then we go to the 6, but most people by the end of this course will go straight from here to here. Just multiply the constant by your power and keep moving on. Last but not least, given f of x equals 2x times the cube root of x, find f prime. Well, before we do that, we should rewrite our f of x as 2 times, I'll put x to the first just to keep everything neat and tidy, and then don't forget the cube root can be written as x to the 1/3. f prime of x. Alright, well, the 1's going to come down and multiply by the 2 and keep it 2, reduce the power by 1 to get 0. Plus 1/3 x, ooh, and this is the tricky one, 1/3 minus a whole is not negative 1/3, right? Think of it as 3 over 3, that's going to be negative 2/3, so negative 2/3 here. Cleaning this up slightly, this is 2 times x to the 0th, which is 1, so 2 times 1 is just 2, and then we'll do this all together. We drop x to the 2/3 down, and then it becomes the cube root of x squared, right? That's the same thing as x to the 2/3. If I could write this in the correct order, that would be right there. And that is our probably simplified form. Now, the last 2 pages are practice problems. This second page I'm going to go through pretty darn quickly, but I would ask please that you try it on your own since it really is designed to be done that way. You'll notice in terms of quick instructions that columns 1 and 2, there's no calculus involved. This is all Algebra 1 and Algebra 2 stuff. They're just asking you to rewrite these as either something to a power or using a fraction and a radical, so using like a square root symbol. 3 and 4 are the derivatives, right? They're going to ask us to take the derivative of this column, right? So right here. And then once we have that derivative, they're going to ask us to rewrite it over here on some of them. Not all of them have to be rewritten. And you have a nice answer bank over here too. You have the power form answers. Well, these are our power forms, right? They're clearly stated as that. And then you have your fractional and radical answers here. So those are going to fill up these too. So again, I'm going to go through it, but again, I would really suggest that you do this on your own. It is not crazy difficult, and it'll save you a bunch of time watching the video. You can check the answers at the end. Let's rock and roll. Fraction and radical, rewriting this as a power form, it's going to be x to the negative first, x to the 1/2. Going the other way, this is going to be negative 1 over x squared, right? Writing that as a fraction. This 2 is a constant, and this is going to be brought down, so it's going to be 2 that stays up top, and it's going to be the square root of x when we drop that down. X to the 1/3 is the same thing as the cube root of x. This one's a little trickier. I think this 2 and 3 can be written as a 2/3, and then this is x to the first, and this is x to the 1/2. Well, don't forget, when you have two bases multiplying, you add the exponents, so it's going to be x to the 1/2 or x to the 3/2. That one's definitely tricky. This one's not as bad. X to the 2/5, remembering that this 5 goes underneath the exponent. And then the rest of these, we have to work backwards. That one's weird. We'll get back to that later on, I think. Let's go ahead and go to our second column. They want the derivative of our power form. So the derivative of our power form, the 2 comes down and multiplies with a 3 to get 6. X, reduce the power by 1. 2x, well, the 1 comes down, becomes 2, and this is x to the 0th now, which is really just 2. You're going to get used to understanding that 2x, the x just drops off and it becomes 2. Let's continue. The derivative of x to the negative first, negative 1, x to the negative second. And then we, of course, could rewrite that as a fraction and a radical, negative 1 divided by x squared. Moving on through, this becomes 1/2 x to the negative 1/2, which is fine as an answer, but if they ask you to rewrite it, 1 over 2 times the square root of x. The negative 1 that's here, the negative 2 is going to multiply with to become positive 2 and then reduce the power by 1, or 2 divided by x cubed. The 4 is going to multiply by a fourth, and 1/4 of 4 is 1. X and then reduce the power by 1. X to the negative 1/2, well, let's see, negative 1/2 times 2, half of 2 is 1, negative times positive is a negative, and then reduce the power by 1. Rewriting this, it drops down, and I think this is going to become the square root of x cubed. 1/3 x to the negative 2/3, we did this one on the previous page, or rewriting. 1 divided by 3 times the cube root of x squared. 3/2 times 2/3, those are reciprocals. I think when reciprocals multiply, they make 1, and then reducing 3/2 by 1 gets us down to 1/2. That's just the square root of x. Nice. 2/5 comes down. X to the subtract 1, I think that's negative 3/5 there. That seems pretty gnarly. When we rewrite, the 2 stays up top, the 5 is already in the denominator, and then we have the 5th root of x cubed. I want to double check that. Did I get it right? I did. That's a y over there. Good. I'm glad that matches. I was a little worried. Now, these last 3 look like they're going backwards. Really stepping it up. I think one of them we can do quickly. This one we can rewrite. That's negative 6 over x to the 4th. What about the other way? Well, we have to think. The derivative of what would be 3x squared? Well, we'd have to add 1 to the power. That's x cubed. And then think, well, is that the right answer? Well, sure, the 3 comes down, that's where the 3 came from. You reduce the power by 1. What about the 6? I think we saw another singleton answer 2, and 2 came from 2x. So I think 6 just comes from 6x. The derivative of 6x is 6, or think the slope of the graph 6x is 6. This one's a little bit harder. We have to add 1 to the power here, so x to the negative 4th, I think that becomes x to the negative 3rd. Checking, negative 3, x to the negative 4th. Yeah, we're pretty close there, but how did they get 6? Well, 3 had to multiply by something that left us with 6. 3 times what is 6? I think 3 times 2 is 6, isn't it? 3 times 2, yeah, I think that works. If we try it, we get negative 6x to the negative 4th. Yeah, awesome. That one's tricky. And then how would we rewrite this? Well, this is 2 over x cubed. I'll let you fill in the riddle on your own. It is awesome, of course, as are all math riddles. Why do derivatives never grow old? Well, you're going to have to match these over here. If you want, you can comment with the answer, or you can ask me if you got it right, but it'll spell out words, so you'll know if you got it right. Last page. These 5 or so problems are really designed to help you prepare for your independent practice. You have a few like this, so let's get to it. Find the derivative of the following function. Well, we have lots of individual terms here, and we know one of our rules says we can just find the derivative of every term. I'm going to color coordinate this so you can keep up with each of them. 2w cubed, 3 multiplies by 2 to get 6, w squared. Easy enough. Our yellow one, 2 multiplies by 3 to get 6w. 10w, well, this 1 is going to multiply by 10, and then the power is going to end up becoming 0, and the w is going to cancel out, so I think the derivative of 10w is just 10. And last but not least, pi squared. Ooh, pi is a constant, trying to trick you here, right? This is all a constant, it's 9 point something, and the derivative of a constant is always 0. And there is our answer. Let's keep going. Find an equation of the line tangent to the given curve at x equals 2. Oh, we can do this. This is tangent lines. We could do this last class and the class before. So I'm going to call my tangent line t of x. And remembering the format of any tangent line of your HK form, right? X minus 2. We're going to need to find, this is y. To use function notation, I'll just call it y of 2. And how do we find the slope of this line? Well, we just find y prime of 2. Let's start with y of 2. I think that one seems a little easier. Y of 2 is just going to be 2 cubed minus 2 squared minus 2 minus 1. This is 8 minus 4, which is 4. 4 minus 2 is 2. 2 minus 1 is 1. Easy enough. Maybe I can even fill in my tangent line down below here. X minus 2 and plus 1. Nice. How do we find the slope at 2? Well, this is where things can get a little dicey. You might be tempted to evaluate 2 in here first. Oh, we just did that. That's 1. And then you're like, then I'm going to take the derivative because the derivative finds the slope. But if you get a value over here, which you'll always do if you plug a number in, and then take the derivative of a constant is always 0. So what we'll need to keep in mind is that when you're finding derivatives, you want to find the derivative function first before you evaluate anything. So let's go ahead and find y prime of x, the derivative function. Well, we're just going to take the derivative of each individual piece here. The derivative of x cubed is 3x squared minus 2x. There's an invisible 1 here, so this becomes minus 1, and then the derivative of negative 1 becomes 0. There's my derivative function, which can be used to find any slope at any point. I want to find the slope at 2 on this crazy x cubed graph. So we evaluate 2 into our derivative function. We'll have a little mental math ahead. 2 squared is 4. 4 times 3 is 12. 12 minus 4 is 8. 8 minus 1 is 7. And so the equation for my tangent line is here. Well, how could you see if you're right? Well, one really easy way is to pull up a calculator or Desmos or something and just graph the original function, this x cubed minus x squared minus x minus 1, and graph the tangent line. And if this tangent line looks like it's bouncing off this cubic function at the point 2, 1, then you did it right. If you didn't, you probably just missed a sign somewhere. It's nothing too bad, but I'll leave that for you to check on B. Your independent practice has you do that a couple times, and I would ask that you do. And then what you're going to do on your paper is you're literally just going to sketch the graph that you saw. Right? So you're going to use your graphing calculator, and you're going to make sure, and let's pretend that this looks something like this. It probably doesn't. You're going to make sure that your tangent line t of x bounces off. So I'd call this t of x, and I'd call this y over here, and this is what I'm looking for on your independent practice on those part B's, an actual sketch. It should be the right sketch. This one is probably not right, but either way, you get the idea. Moving on to 3. Find all points on this bizarre graph up here at which the tangent line is horizontal. Ooh, this one's getting strange. Well, let's go ahead and maybe picture what has to happen for tangent lines to be horizontal. And I think to do that, I'm going to go ahead and pull up this graph. Now, you don't need this graph to do this problem. However, visually, I think it makes a lot of sense. So let's just take a look at this piece over here. If I wrote a tangent line through this random point, my tangent line would be going up. Right? It's going up. That means the tangent line would have a positive slope, and it definitely wouldn't be horizontal. If I wrote a tangent line through this point, the tangent line would be going down. The tangent would have a negative slope, and it also would not be horizontal. Horizontal side to side. Well, what point or points on this graph can you see where the tangent line would be going horizontal? Well, I think they're going to be at these relative maxes or mins, right? This right here would have a tangent line that would perfectly bounce off our graph. Sure, it touches another point, but it meets our qualification for a tangent line. It is going to end up being, if you have a tangent line here, it's going to look parallel to this graph as we get infinitely close to that point. Horizontal tangent lines are tangent lines that have what kind of slope? Well, they're tangent lines that have a slope of 0, because horizontal lines, side to side, have slopes of 0. So maybe we could reinterpret this question, and instead of at which the tangent line is horizontal, we could maybe say at which the tangent line has a slope of 0. But how does that help us? Well, think back to our tangent line. Our tangent line is created by our x minus a plus f of a, some point over here. But this slope, right, a slope of 0, we say is f prime of a. So what they're really saying here is that f prime of a has to be 0. Or another way to interpret it is find the f prime function, find the derivative function, and figure out what value, when you plug it into the derivative function, gives us an output of 0. And I think maybe this will be more clear if we actually put some numbers into it. So here's f of x. Let's go ahead and find f prime of x. This is going to be, let's see, 3 times 2, that's 6x squared. 2 times 3, that's minus 6x. Minus 12x, so minus 12, and 4 just becomes 0. We want to know what input, right? A is our input, and our inputs, of course, over here are our x's. What input creates an output, here's my output, of 0? Or basically, when is the derivative 0? So, let's set it up. When or what x value will create an answer of 0? Solving this could be a little tricky. You may have be a little rusty in your algebra. I'd suggest first that you factor out a 6 from everything. I think that'll make our lives a little bit easier. And then maybe you'll remember that we need to factor this, right? So this becomes x minus 2 times x plus 1, two numbers that multiply to make negative 2 but add up to make negative 1. And then to solve, we just set each one of these equal to 0, and maybe I'll show this up here. We have x minus 2 equals 0, or x plus 1 equals 0. So we find two values of x. We find 2 or negative 1. Which would be nice if we could just circle those, except they said find all points, and x values aren't points. Points are x comma y. So we're going to take our two x's, 2 and negative 1, and how do we find the y's that go with them? Oh yeah, we take those x's and we put them back into the original equation because we want points on the graph of f. We take 2, put it into the original equation, and have to do the math. Now, just to make sure I'm right, it seems like an x value of 2 and an x value of negative 1 should be our horizontal tangents. Oh yeah, x value of 2, that's negative 16 by the way, and an x value of negative 1 at 11 are the horizontal tangents. So when you do the math with 2, you'll get negative 16. Do the math with negative 1, you'll get 11. These are the points that are being looked for. Let's try one more. This one will go a little faster. Find all points on the graph at which the tangent line has a slope of 60. Well, the tangent line's slope is, of course, this f prime of a, and a slope of 60 means the output has to be 60. Super similar to before, except now we just need to set 60 equal to our f prime equation. So 60 equals 6x squared minus 6x minus 12. To make our lives easier, we might divide both sides by 6 first. X squared minus 1x minus 2. And then we know in order to solve something like this, in order to factor, our equation needs to be equal to 0. So we have 0 equals x squared minus 1x. Remember, we're subtracting 10 from both sides. That was supposed to say minus 10. So this is minus 12, and then we factor. 0 equals x minus 4 times x plus 3, two numbers that multiply, two numbers that add, and then solve. And I imagine most of you know it's just the opposites here. Very exciting. And last but not least, we find our points. 4 comma what and negative 3 comma what. And again, these points are found by substituting 4 and negative 3 into this equation. You can find them on your own. It's nothing too crazy. Use your calculator, but in the interest of time, we're going to keep going. Two problems left. 4 and 5. Suppose that f of negative 2 equals 6 and f prime, they're giving us the derivative at negative 2 is negative 9. Let g be a new function that's created by adding x squared and f of x together. Write an equation of the line tangent to g at x equals negative 2. Okay, well, this just seems like a tangent line, and we should hopefully be getting used to our format of a tangent line. Opposite of x. We are writing this tangent line to g, so I'm going to have g of negative 2, and my slope is going to be g prime of negative 2. There's my HK form. Let's find each of these. G of negative 2. I'll do this one in red, I think. G of negative 2, where's my function g, that's up here, is equal to negative 2 squared plus f of negative 2. Well, negative 2 squared is 4, and f of negative 2, oh wait, they told us f of negative 2 is 6. 4 plus 6, that's 10. My tangent line is halfway complete. It's going to be something times x plus 2 plus 10. Cool. What about our g prime of negative 2? Well, before we actually evaluate g prime at negative 2, we probably need to find the equation for g prime of x. Okay? Our equation for g prime of x is the derivative of this. Ooh, and this one's important. The derivative of x squared, I bet we're starting to get comfortable. 2 times 1 is 2, x to the first, just 2x. But how do we show the derivative of f of x? Well, because f of x is a vague equation, they didn't actually give us an equation, we actually get to be really lazy here. The derivative of f of x is just f prime of x, right? We don't know the equation, but we notate the equation as f of x, so that means we don't know the derivative, so we're just going to leave f prime of x to hang in here until we can actually know the derivative. But at least it gives us some direction. The derivative of f of x is f prime of x. Same way, the derivative of g of x is g prime of x, right? Nothing new there. Well, now that we're here, we can evaluate g prime of negative 2. 2 times negative 2 plus f prime of negative 2. We get negative 4, and then f prime of negative 2. Oh, they gave us that. What a clever problem. So minus 9, which is negative 13. And there we have it, our final tangent line. 5, I think, is probably more of the same, but there's a couple more pieces to it. So let's go ahead and read through. So we know the line tangent to the graph of f at x equals 2 is this tangent line. Now, I want to pause quickly, and I'm not quite sure why there's an extra and here. Also, suppose the line, okay, well, that's awkward. So let's take a look and think about the graph of f at x equals 2. So here is x equals 2. I have no idea what the graph of f looks like. It doesn't really matter. But I know a couple things about what happens at 2. First, there's a tangent line there, 4x plus 1. That starts here and it goes up 4 over 1, up 4 over 1, something like this. Here's my tangent line. That line, and this is y equals 4x plus 1, is tangent to the graph of f. Well, what does that mean then? Well, I can probably sketch in the graph of f, and I know that the graph of f has to do something like this, and they have to share that point. Why do they have to share a point? Well, that's the point where the tangent line is tangent to the graph of f. So if we wanted to know the point on the graph of f, 2 comma f of 2, we could just find the point 2 comma what on the tangent line. Well, if we evaluate 2 in here, 4 times 2 is 8, plus 1 is 9, 2 comma 9. So this tells us then that f of 2 is 9, because they have to have the same point at their point of tangency. We even know one further thing. And the further thing is our definition of tangent lines is that a tangent line shares the slope on the graph of f at their point of tangency. That's where we zoom in really far and they look like they're the same. They're parallel to each other. They're the same slope. So if I was asked to find f prime of 2, the slope of the red graph at 2, and I didn't have an equation, well, we already have a tangent line. And so whatever the slope of the tangent line is the same thing as the slope of that equation. Well, you know how to find the slope of lines. To find the slope of lines, you just look at the value multiplying by x. The slope of this line is 4. And so that means on the red graph, the slope is also 4. So I'm going to record those couple pieces of information because having done this a few times, I know they're going to be important. They are telling us that f of 2 is 9. And again, that comes from just evaluating the tangent at 2. They're also telling us that f prime of 2 is 4 because the slope of your tangent is the same as the slope of your graph of f. Alright, well, let's look at this other one. Also, suppose, and I should have showed that this is in red, suppose that the line tangent to the graph of g at x equals 2 has a slope of 3 and passes through this point. Well, we should probably do this one as well. Very similar to what we did before. We need to go 0, negative 2, slope of 3. We'll do something like this. Here's 0, negative 2. They told us there's that point on our tangent line. I'll keep the tangent line in black here, I think. And it has a slope of 3, so up 1, 2, 3 over 1. Up 1, 2, 3 over 1. So this right here, not great, but oh well, is my tangent line. They weren't even nice enough to give us a tangent line, though. That is rude. Luckily, we're great at writing this. And actually, because we know the y-intercept, we could write this in mx plus b really quickly. Slope of 3, y-intercept of negative 2, tangent line. Awesome. We also know that the graph of g has to come through here, do something, who knows what, but right here it better bounce off and then continue going somewhere else. That is not very pretty. Maybe I'll make it look like that. That's a cute little tangent line. Okay, so this is tangent right here. They look like they're parallel at that spot. Very exciting. What do we know about this? Well, very similar to the last one. First, if we wanted to find the value of g of 2, right, that's like the point, what happens at g when x is 2, we could just find what happens on here at 2. This is the point 2 comma, if we plug in 2, 2 times 3 is 6, 6 minus 2 is 4. That tells me then that g of 2 is 4, and I'll record that over here. G of 2 is 4, because the tangent line and the original graph have to share that point at their point of tangency. What else do we know? Well, we also know g prime of 2. G prime of 2 is the slope right here, but since a tangent line has a constant slope, all lines have a constant slope, and this one has a slope of 3, then we know that g prime of 2 is 3. It might seem weird as to why I started with all that, but again, I've done this problem before, and so I'm just trying to get everything out of the way so we can do the actual calculus part pretty quickly. So let's get to it. Find the equation of the tangent line to the graph created by doing f of x minus 2g of x at x equals 2. Alright, maybe you'll start to see why all this is useful. We need a tangent line, and our tangent line, they call it to this graph of y up here, is going to be found by doing y prime of 2 times x minus 2 plus y of 2. Same format for our tangent line every single time. The derivative is the slope, the y value is the output. So how do we use this? Well, same thing as before. I'll keep my tangent line way down here. We get a blank in here, x minus 2, and another blank that we'll fill in shortly. So let's do our output first. Our output here, y of 2 I'll do in yellow. Y of 2, they gave us the function as f of 2 minus 2 times g of 2. F of 2, luckily, we know is 9. And g of 2, we know is 4. So 9 minus 8 is 1. We know the y value on this bizarre graph of y is 1. We also need our derivative, and the derivative I'm going to go ahead and do in purple. That's going to be my y prime. So y prime of x first, we don't plug in 2 yet, is going to be the derivative of what's up here. Well, the derivative of x we notate as f prime minus 2 times the derivative of g we notate as g prime. Notice I didn't do the derivative of this constant because it's multiplying by a function. That's one of our rules on the previous pages. Keep the constant out front. We need to find y prime of 2. That's f prime of 2 minus 2 times g prime of 2. F prime of 2, well, let's see. F prime of 2, oh, we have that up here. That's 4 minus 2 g prime of 2 is 3. So that becomes 4 minus 6, which is negative 2. And we have our tangent line. This is a pretty complex problem, putting lots and lots and lots of pieces of information together, but it is a very good problem. You will have one like this on your independent practice and maybe one like this on your knowledge check. Good luck with everything. Keep it up. Make sure you're asking questions if you get stuck anywhere. I wish you the best.